Hey, what's up guys? Hope you're doing well. I'm Arvind from PrecisionDataScience. Today we're going to be working on Mercedes Benz Greener Manufacturing dataset. In this dataset, we have complex features related to Mercedes Benz car testing system, and we're going to be building a machine learning model to predict the time taken to pass the test, which in turn contributes to faster testing and results in low carbon emissions. So without further ado, let's dive into the video. First, we're going to ignore the warnings to have a cleaner output and then import NumPy and pandas to work on the array data and data frame. We will read the toCSV file using read_CSV method and assign it to a data frame df and df_test. Since IDs are unique to each car and may not play a role in deciding the time required to pass the test, we can drop these columns with the drop method. Before that, we're going to assign the ID values from the test data to a new variable test_ID so that it can be used to make predictions on the test IDs. We'll display the first few rows for each dataset using head method. And here we can see the features from X0 to X385 in both train and test set. One thing that distinguishes the train data and the test data is the presence of Y column in the train data, which shows the time required to pass the test. df.shape method shows the number of rows and columns, and we have 4209 rows representing each car and 377 columns representing each parameter. For the test set, again we have 4209 rows and 376 columns. Using select types, we're gonna select the categorical and the numerical columns and assign it to a separate dataset df_cat representing categorical columns and df_num representing numerical columns. We'll apply a similar approach to the test set. With isNull.sum.sum method, we're gonna see the number of missing values in each dataset. As we can see, there is no missing values in the train data or test data. With the describe method, we can observe the min, max, mean, and standard deviation for each column. Here, some visible columns like X11 have a standard deviation of 0, which means that the variance is also 0, thus not contributing to the time required to pass the test. Next, we can see the top 5 rows of both categorical dataset by passing the head method, and we can see the columns filled with encoded values using alphabets. We're going to see the top 5 rows of the numerical columns, and here we can see that the columns have values ranging from 0 to 1. In the train set numerical columns, we have an extra column Y, which acts as a target column. We're going to separate the Y column and assign it to a variable Y and drop the column from the training dataset. With the head method, we can see the Y column has vanished. Next, we're going to check the variance across the train numerical set and use a for loop to append the columns with 0 variance to an empty list variable variance 0. We'll apply similar approach to the test set and append the 0 variance numerical columns to an empty list variable test variance 0. Next, we'll select all the columns with 0 variance either in the train or test set and drop them from both train and test set. This is done to ensure that the train set and the test set have same features for building the machine learning model. With the head method, we can see that the train set and the test set have same columns. And with any unique method, we can see the train set features and the test set features have only 2 values, that is 0 and 1. Next, we'll move on to the categorical set. Head method shows 8 categorical features that are present in the train and test set. For machine learning model to work, we need to convert the categorical features to the numerical features. For that, we'll be using label encoder. We'll import the label encoder from the scikit-learn library and instantiate the label encoder. To apply label encoder to each categorical column, we'll run a for loop across the train set and fit the data to the combined train and test set. After fitting, we'll transform the columns in training and test set. With the head method, we can see the transformed numerical values. Since each column have different range of values, we're going to apply one more transformation, that is min-max scalar, to bring the values between 0 and 1. We'll import the min-max scalar from the scikit-learn library and instantiate the min-max scalar. We'll fit transform the training set and transform the test set. After transforming, we can see that the values range between 0 and 1. We can cross-verify this with describe method. For both train and test set, we have a minimum value of 0 and maximum value is 1. Since numerical and categorical columns have been optimized for machine learning model, we can combine the columns to create a feature set for training the machine learning model. We will apply a similar approach to create a test feature set. Since the number of features are high, implementing the machine learning model will be challenging and tedious. In order to simplify the process, we're gonna use principal component analysis to reduce the number of features. Principal component analysis, or PCA, is a dimensionality reduction technique which is used to project high-dimensional data to low-dimensional space while retaining much of the original variance. We'll import the PCA from the scikit-learn library and instantiate the PCA with 15 components. 15 is just an arbitrary number, and we can make it more complex by increasing the number of components, but then the training time will also increase. We will fit transform for the training data and transform for the test data. Now, in order to build the machine learning model, we will split the training data into train and validation set so that we can verify the model predictions and optimize it further. We're going to import train test spread from the scikit-learn library and split the training data into train and validation set with a validation size as 20% and a random state to maintain consistency. Now let's shift gears to machine learning model implementation. Here we are using XGBoost Regressor, which uses gradient boosting method by combining weak learners with a learning rate and a regularization technique to create a strong model. We'll instantiate the model with these hyperparameters and a random state of 397. The hyperparameters were taken from my previous case of multi-class obesity prediction and did a bit of tweaking to get the optimized result. We'll fit the model for the training data. After the model learns by fitting the data, we're going to predict the label values for the validation set. For evaluation, we're going to import mean squared error. We will import the mean squared error from the scikit-learn library and try to find the values by comparing the predicted and validation set values. We will calculate the RMSE by taking the square root of mean squared error, and here we are getting RMSE of around 8.7, which is a good value. If you want further improvement, you guys can try to tweak the parameters or use a random search CV to get better results. Next, we'll make the prediction for the test features and create a data frame with the test IDs. We will export the test set with predictions to a CSV file for submission. If you have the test target values, you can compare the predictions to find the test RMSE and let me know your results in the comments. So that's all I have today, guys. If you enjoyed this video so far, please like the videos, subscribe and hit the bell icon to see more content. Thank you.